Hey guys, we're going to cover the final section that we're going to go into detail with on chapter 13. This one is called the physical pendulum, very similar to the simple pendulums formulas, just some adjustments we have to make. The difference between a physical pendulum and a simple pendulum is the fact that we'll need to consider moment of inertia. If you remember back to the simple pendulum, would be an object on a string, rope, cable, where the string or whatever we were swinging on was considered massless, and therefore we only had to consider the periodic motion of the mass hanging at the end of it. But we could have physical pendulums where whatever connects the swinging mass to the rotational origin point maybe has significant mass or is a solid object or something like that. And then we got to consider the moment of inertia of the whole system rotating, and that's where torque comes in. So looking at our diagram down here, we have a fixed position. This is the rotational axis. Some mass at the end of maybe a rod or whatnot that we can't ignore its mass. So just as we defined torque in the past, if you recall, torque, or in other words, what's necessary to rotate an object, is equal to Fr sine theta. Now we're just going to define it a little bit differently here, but it's from that same formula. If we have a swinging object, physical pendulum, the force that's causing the torque is going to be equal to the weight of the system, mg. And D is going to just be defined as the distance from the point of origin out to the center of mass of whatever is hanging on it. But maybe this could be like a rod where nothing's hanging on it, so it would just be like the length of the rod or something like that. And sine theta, and you should recall that sine theta is part of the original torque formula for Fr sine theta. Now, because there's a sine theta there, this is showing that this is a restoring torque. That's where the negative comes in. Just like when we talked about restoring force with simple pendulums and spring pendulums. And written as is, the torque is proportional with the sine of theta, not theta. So we could do the same thing we discussed back in the simple pendulum section, where at very small amplitudes, roughly between 0 and 15 degrees, in radians, the sine of theta is approximately equal to theta itself. So this again is only going to be a system that is in SHM. You could use the formulas below if it's at small amplitudes for a physical pendulum. So if we could approximate that at small amplitudes, I take that formula for the restoring torque and I just write theta instead of sine theta. Now, if we recall that if that is the only torque on the system, Newton's second law for rotation tells us that the sum of all torques, or just that torque now at small amplitudes, is equal to I times alpha. So we make that connection. And that fact yields some adjusted formulas, particularly the two we're going to care about the most in this section are for the angular velocity and the time period involved with physical pendulums. Now, also, though, all the other formulas for SHM could be adjusted with these two. And you'll notice that now we have a moment of inertia of the system I in there for physical pendulums of small amplitudes. So we'll need to remember some formulas for moment of inertia when doing our problems. And now we're going to go over to an example out of this section. it says in example 13.9, suppose the body in figure 13.3 is a uniform rod with length L. All right, I'm not going to flip up to that figure. What matters here is we have a uniform rod swinging back and forth, pivoted at one end. We just want to find its period of motion. Pretty simple. All right, so remember the adjusted period formula is 2 pi square root I divided by mg times d, right? So we just need the moment of inertia of the system. It's just a rod. It does not say that there is a mass hanging at the end. If there were, though, we'd treat it as a point mass, and we should be capable of finding the moment of inertia of the system of a point mass and rod. But this one's saying just a rod. So if we go back to earlier rotation chapter, if we don't remember some of these values, remember there's a table in that chapter that has some common moment of inertia values, and a rod fixed at one end is 1/3 ml squared. So that's the moment of inertia right there. That's why that's plugged in. Another key feature of this, let me flip back to the original formula here. Since there is not a mass at the end, all right, let's look at the original example where we had a mass at the end of this physical pendulum. The center of mass from the origin is what D is defined as. So since there is just a rod swinging, we use its own center of mass, which is in its geometric center, which would be half of its length. So that's where this L over 2 is coming from, to avoid any confusion here. So that D in that formula represents like the distance the center of mass of the system is away from that point of origin where it's swinging from. Now all we got to do is clean it up algebraically, and the period of this physical pendulum is 2 pi times the square root of 2L over 3G. We could plug in the numbers. For example, of a rod that's 1 meter long and a G of negative 9.8, like always, and this would have a time period of 1.64 seconds. All right, there's going to be a small problem set assigned on this, but this is the last thorough section we are going to cover in this chapter.